One and all. Once again, I welcome you all in this post-lunch session. Again, Professor Shimpi is with us, and he will deliver his technical talk on the topic development of novel nanofibers and their applications. So, Shimpi sir, can we start the session?
Yes, ma'am. Am I audible to all? Am I audible? Slides are...
Yes, Professor. Yes, Professor Shimpi, you are audible.
Yes. My slides are seeing, na?
Yes, we can see that.
Okay. So, good afternoon, one and all. Thank you for, I express my sincere thanks again to Professor Jain, Professor Kirti for inviting me for this second session again. That is today in this session, I would like to discuss about development of novel nanofibers and their application. This is the content of my presentation. This presentation is divided into 5 parts. First part will be the introduction. Second part will be pan zinc oxide hybrid nanofibers. Third part will be pan AGG hybrid nanofibers with synthesis and its application. Fourth part will be pan AGG C3N4 hybrid nanofibers. And the last one will be the copper nickel carbon nanofibers that I will focus on that particular presentation. So as of now, I have already explained about this particular part, that is about the nanofibers, what is nanotechnology. And into this nanotechnology, already we have discussed about its definition, what is meant by nanotechnology. As I mentioned, the size range between 1 to 100 nanometer is nothing but at least one dimension should be in the range of nanometer, and this is the complete scale which I would like to show here. That is from macroscopy to microscopy, microscopy to nanostructure, and like this, the size range is there. And the dimensional size is from that is nanomaterials is having high surface to volume ratio, as well as it requires high porosity. And its dimension is ranging from 0 dimension to 1 dimension, 2 dimension, and 3 dimension. When we talk about 0 dimension, high specific surface area, one dimensional material, light scattering, non-own material. When we talk about the 2 dimensional, that is, we say it is a 2D smooth surface along with high adhesion. And when we talk about the 3-dimensional material, these materials are high carrier mobility. They have the high carrier mobility. And considering this nanotechnology, they have the vast application. When we talk about this particular material, that as already mentioned, that is energy storage to defense, metallurgy and materials, electronics, then optical engineering and communication, then biomedical, agriculture and food, cosmetics and paints, biotechnology and textile. Means this is a complete cycle, big cycle is there, where these nanomaterials are considerably useful for the wide variety of the application. When we talk about these 1D nanofibers, that is 1D nanofibers. One of the participant has asked me about the nanofibers are one-dimensional. Why these are one-dimensional? Because they have the large specific surface area. These materials are advanced. They are towards these materials we can see as an advanced functional material. When we talk about the nanofibers, if I remove this word nano from that particular fiber, suppose I cancel this word nano, and if I talk about only the fibers are very important in our life, because if we take for our health purpose, if we talk about our health purpose, if we take the fibril food, then that will be very good for our health. Fibril foods are very good for our health. Okay, so if we talk about the strength of the material, very high strength material, these materials are very strengthful material. The Kevlar fiber, Kevlar fiber is one of the fiber that is used for the defense application. These are the Kevlar fibers are there. Okay, Kevlar fibers are used for the defense purpose. These beside this, aramide fibers are there. They are made from the amide group. These aramide fibers are very highly strengthful. If we talk about the natural fiber, jute fiber, hemp fiber, then banana fiber are there. These fibers are they are very strengthful material. These are used for the improvement in the properties of properties of the composite, 100 times more compared to the normal material because of the addition of this fiber. These materials are highly porous. When we talk about the complete nanofiber, these fibers are highly porous material. Pore size is very small pore size. If this is the fiber, if I say this is the fiber, and whatever is the pores are there, the pore size is very fine, very smaller size. The porosity is very high, but the size of the pores is very small. Robustness. This material can be easily reusable if you wash it properly. If we treat with the help of the acid, this material can be used number of times. Thermal stability is good, as I mentioned. Mechanical property is very good, as I mentioned. Means 100 times more than the steel. These material, they're like carbon nanofibers. Carbon nanofibers and these normal fibers are having good strength as compared to the other fiber. When we talk about the application of these electrospun fiber, these are the application. This material can be used in the filtration purpose. They are used in the energy storage. They are used in the textiles. But in textiles, smart clothing, protective clothing, fire retardant fabrics can be used. In catalysis, they can be used as a photocatalysis in the photocatalysis reaction. In sensors, these materials are having wide application in the gas sensing, as a chemical sensor, as a piezoelectric sensor. Wide varieties of application are there when we talk about this particular fiber. These are the biomedical fibers. They are used specifically in the drug delivery, tissue engineering, wound dressing. When we talk about medical application, these nanofibers can be used for the teaching, for the teachers. When we operate for any disease, the teachers are being put. These teachers are being given with the help of this nanofiber, and they can be easily dissolved after complete healing of that particular wound. Okay, so now wide ranges of application are there. Method of fabrication of nanofibers. These are the number of processes being put in front of you. That is a drawing, then template synthesis, phase separation, self-assembly, and electrospinning. When we compare these processes as a laboratory or industrial processes, these are the first four are the laboratory method, and this electrospinning is laboratory as well as this becomes the industrial process also. Repeatability in all cases is possible. Maximum processes are very easy. This is very easy, very simple process, very cost effective. Large variety of polymer can be electrospun. Long continuous nanofiber can be possible, but in some cases only short fiber can be possible. But with the help of this particular electrospinning technique, long and continuous nanofiber can be possible, as well as variable ranges of the fiber can be possible. Means like when we talk a single fiber, double fiber, or multi-layer fiber can also be possible with the help of this electrospinning technique. So this is the electrospinning technique. What is electrospinning technique? See, a high voltage power supply that is range from 10 to 30 kilovolt is required. Normally working in the range between 10 to 30 kilovolt. When we apply, this is a complete setup of electrospinning. Here is the drum. This is the drum where we can draw the fiber. This is the connector. This is the searing, and this is the rotor from where this is the compressor from where the searing can be compressed in a normal pressure. Once the searing is get pressed, here is the needle is charged with the help of this crocodile pin. And when it gets charged, what happens? The fiber, the liquid can come from this particular needle, and it can be come over this particular drum, and the fiber can be roll over this drum. And when we take out this fiber, it is like a tissue paper. The tissue paper, it is just like a tissue paper. That is, it is clearly mentioned when a high voltage is applied, we are applying the high voltage with the help of this particular pin. Liquid becomes charged. Whatever the liquid is there inside this particular syringe, that liquid comes from that syringe and it gets charged with respect to this applied voltage, and electrostatic repulsion counterpass the surface tension and droplet is stretched. Whatever the drop is there, here is the drop. That droplet is gets stretched towards the direction of this drum, and at a critical point, liquid erupts from the surface. It will erupts from the particular surface. If the molecular cohesion of the liquid is high stream, breakup does not occur and charged liquid jet is formed. This substrate is a conductive where the fibers are get collected. A conductive substrate is there, normally grounded, which serve as a collector for the electrospun nanofiber. These are served as a collector plate. It is acting as a collector plate. There are the two ways of the electrospinning setup. One is a horizontal and second one is a vertical. This one is a horizontal and another is a vertical can be possible. When vertical will be there, what time the cone will be formed? Cone formation is Taylor. It is called as a Taylor cone. It is like a Taylor cone formation. A Taylor cone is formed like this. It is formation of the Taylor cone. So these are the synthesis. These are the different methods, materials we have synthesized. These are the characterization technique we will utilize. These are the application we will check, and reaction parameters we have. That is the effect of the voltage, concentration of the solution, distance between the needle to the collector plate that we see here. So how we go with this? Optimization of the parameter. Effect of the concentration. What is the effect of the concentration? Because we are drawing the nanofiber, that nanofiber obviously drawn with the help of the polymeric solution. And when we talk of the polymeric solution, that is the concentration of the polymeric solution. When concentration of the solution is 10 weight %. See, 10 weight % solution gives 200 to 400 micrometer size. This is the size. This image itself showing how the viscosity or the concentration of the solution is affecting on the size of the nanofiber. When we talk about 12 weight %, size comes 700 to 800 nanometer. When we talk about 15 weight %, it goes 1 micrometer. Means not too much minimum viscosity is required or not too high viscosity is required, not maximum. Means it should be the moderate viscosity. Viscosity should be the moderate one. So 10 weight % of the solution gives the very fine nanofibers of the range 200 to 400, in between the 200 to 400 nanometer. This is the size. And even though if we look into this particular part, see somewhere there is a formation of the knot like this. This knot is there. If we look into this, there is no any knot, but overlapping is there, but that is not the knot. Here is the overlapping of the fiber, but no knot formation is taking place. If we look into this, see the thickness of the fiber is very high. Here the thickness is very high. Here the thickness is very high, but dispersed uniformly. Everywhere you will get a uniform dispersed nanofiber, but the diameter wise, length wise, it is in the centimeter or like this, or in millimeter. But diameter wise, it should be in the form of the nano. Therefore, it is called as a nanofiber. Diameter wise, these materials are in the size of the nano, and therefore these fibers are called as a nanofibers. When we talk about another parameter, the parameter is effect of applied voltage. The range of the voltage applied is 10 to 30 kilovolt. This is the range. But when we look into this, which voltage gives a very fine size? See, 15 kilovolt we are talking here. This gives 344 plus or minus 51 nanometer size. If we look into 20 kilovolt, it gives 323, and 25 kilovolt gives 331. Means 20 kilovolt, 25 kilovolt gives very less size of the nanofiber as compared to the 15 kilovolt. And amongst 20 and 25 kilovolt, 20 kilovolt gives the moderate size, that is in between 323 nanometer to 350 nano, in between that. But if we look into this, this is better option to go with 20 kilovolt. This is the moderate range of the voltage which we have to apply. Okay. Again, here are the some big patches are there. If we look into this, the complete branch fibers are there. Because of this branch fiber, again there is a big node is there, and here a uniformity is there somewhere because of the instrumental effect or person handling that particular instrument that is affecting. That is also the one part where the control size cannot be possible from that particular nanofiber. Then distance between the tip to the collector plate. What is distance between the tip to the collector plate? This is the distance between the tip to the collector. This is the tip of needle, and this is the collector plate. This distance is also one of the important parameters. So that's why it is we mentioned distance between the tip to the collector plate. If we keep the distance 15 centimeter and if we keep the distance 20 centimeter, what will happen? The size is big here, 438 nanometer, but 20 centimeter gives 368 nanometer size. If we go again 25 centimeter, what will happen? The fiber will very small and it will break. There is a chances of breaking of the fiber. Continuity will break here. But at 20 centimeter, the fiber will draw continuously without any breaking, without any formation of the knot. So important parameters is the viscosity of the solution. Second one is the processing condition, that is applied voltage. Third one is the physical parameter like distance between the tip and the collector plate. Okay, as well as the room temperature is very much important. Moisture may be there. If moisture will be there, then the drawing of the fiber is very sticky, and there is a formation of some layer by layer formation is possible, and you will not get the proper fiber. So first we go with the fabrication of this. Before that, I would like to mention here the preparation of the solution of the pan. If you are drawing the pan nanofibers, and with the help of the pan nanofiber, if any operation is there, that method was to utilize. 10 weight % of polyacrylonitrile solution was prepared by dissolving it into dimethyl formaldehyde solution. We will prepare solution of pan polyacrylonitrile, that is a polymer is directly purchased from the market. Otherwise, you can synthesize that pan in your laboratory with the help of the acrylonitrile as a monomer, and go for the condensation polymerization. You will get the pan that is a polyacrylonitrile polymer. Then prepare the solution into DMF. This will be the solution. Maintain the viscosity. Moderate viscosity should be there. It should not be too much high. If you want to measure the viscosity, you can use the Oswald viscometer to measure the viscosity of the solution. Okay. Then you should stir this solution for 3 hours so that there should not be formation of the gel. Gel should not be formed. Don't avoid the formation of the gel. Okay. No need to go for the overnight. Only 3 hours is sufficient, and put the solution for at room temperature, the homogeneous solution. Then the prepared solution was transferred to the this one, that is a searing. Fill the searing with the help by this solution, with the help of this solution, that is a pan and pan solution. And when you start to draw the fiber, flow rate should be 1 ml per hour. At voltage 20 kilovolt, with the tip to the collector distance should be 20. As I mentioned, that is a 20 centimeter, then 20 kilovolt, and flow rate will be 1 ml per hour. 1 ml should be there. Okay. Finally, fibers were collected over the collector plate, dried it properly, and transferred into your this one container where in which you want to store that particular fiber. That container should be there, and that container should be the moisture-free container. After that formation, what you have to do, we are trying to do decoration of zinc oxide over the pan. That is a pan fiber is there. This is the pan fiber. These are the pan fiber. Over that pan fiber, we are trying to decorate these zinc oxide nanorods or zinc oxide nanoparticles. This is called as a decorated, means zinc oxide pan polyacrylonitrile fiber decorated zinc oxide nanoparticle. Therefore, it is called as a pan ZNO hybrid nanofibers. Whatever the solution is there, you should prepare the solution of pan, then prepare the solution of zinc oxide nanorods, then mix both this solution together and put into the searing, and apply the pressure Allow the solution to pass 1 ml per hour at 20 kilovolt by keeping the distance between the tip and the collector plate 20 centimeter. Once the fiber can be drawn, dry it at 80 degrees centigrade. You will get pan zinc oxide hybrid nanofiber. Then fabrication of pan AGG hybrid nanofiber, polyacrylonitrile silver graphited hybrid nanofiber, silver graphited hybrid nanofiber. Initially, graphite can be converted into the graphene oxide by the Hummers method. Then into that solution, add silver nitrate under controlled sonication for 1 hour. What will happen? AgNO3 is get dissociated as Ag plus and it get reduced to Ag0. Okay. Once it get to reduce to Ag0, it is come over the surface of the pan. That is a graphene sheet is there. Okay. Here the sodium borohydrate at 95 degrees centigrade. Silver graphited. After that, prepare a solution of the pan. Prepare the solution of silver graphited nanoparticles. Mix both the solution. Transfer into searing. Draw the fiber. And whatever the fiber will draw, that fibers are called as a pan AGG hybrid nanofibers. Am I audible, sir?
Yes, you are audible.
Yes, yes. Okay, thank you. Okay, next. Fabrication of pan AGG C3N4 hybrid nanofibers. This is polyacrylonitrile silver graphited graphitic carbon nitride nanofiber. These are GC3N4 is nothing but the graphited carbon nitride nanoparticles. Silver nanoparticles decorated over it, and then the decoration of AGG C3N4 or pan nanofiber. So how we do synthesize this? Synthesis of graphited carbon nitride. With the help of the urea, we take the some molar ratio of urea, pyrolyze at 550 degrees centigrade, ambient pressure will be there. It gets graphitic carbon nitride. This is the powder we have obtained. All these materials we have synthesized in our laboratory. Okay. Then this bulk graphited carbon nitride solution been prepared under sonication. Okay, with the help of the ultrasonic probe. Then solution of silver nitride mixed together. Then hydrazine hydrate is being used as a reducing agent here. Then decoration of silver nanoparticle over the graphited carbon nitride is been observed like this. Then this complete solution is been transferred and mixed into the polyacrylonitrile solution. After preparing this solution, we transfer this into the searing and we are drawing the fiber that is called as a pan AGG C3N4 hybrid nanoparticle, that is pan silver graphitic carbon nitride nanoparticles. Then fabrication of copper nickel carbon nanofibers. Here we use copper nitride and nickel nitride. These are the precursor solutions we are using with the help of the pan, and directly transfer the solution into the electrospinning setup. These we have selected the ratio 1:1, 1:2, 1:3 like this. And after drawing, the pan copper nickel nanofibers are formed. These are the pan nickel nanofiber. We stabilize this material first. After stabilization, we put for the carbonization, And once the carbonization is done, carbon nanofibers are formed with the help of the tubular furnace. Now the characterization. These are the characterizations we have done for pan zinc oxide nanofiber. This is for zinc oxide, XRD for the zinc oxide. This is XRD for pan. And the combination of both these peak, both the crystal plane itself showing the formation of pan zinc oxide nanofiber. When we talk about the FTIR analysis, zinc oxide showing at peak at 891 to 718 centimeter inverse, while pan is showing the functional groups at 2928, 2247, 1642, 1456 centimeter inverse. And when we prepare the pan zinc oxide nanofiber, we observe that there is a presence of this peak also, along with the presence of the peaks from the pan. Means this is the combination showing that pan zinc oxide nanofiber. This is the XPS study. XPS study itself showing again the formation of this complete pan zinc oxide nanofiber in presence of pan and zinc oxide. The binding energy itself predicting the in adherence with the standards which we required with presence of the inner and outer layer cells. These are the deconvoluted spectra. That is O2 minus in rosite structure of hexagonal helium 2 plus ion array shows 532 electron hole. Oxide ions in crystal lattices. This is for the zinc oxide nano rods. This is for pan nanofibers, and this is for pan zinc oxide nanofibers. And this presence of binding energy itself showing the formation. This is well, we have separated the deconvoluted spectra from the convoluted spectra. This is the UV DRS study. This is with the help of the UV spectroscopy under DRS mode. We can able to do the UV spectra for the solid material also. So here zinc oxide is showing the binding energy 3.40 electron volt, while to that of pan zinc oxide it comes to 2.10 electron volt. These are the FESM images. This is for the zinc oxide nanorods. Very fine and sharp rods are there. This is for only the pan nanofiber. This is for pan zinc oxide nanofiber. And if you look into these particular patches, these are the patches. That patches are showing the adherence of that particular zinc oxide nanorods over the surface. Here some patches are there. Here are the some patches that breaks the fiber here. This same image itself showing this is the complete patch of the zinc oxide nanorod. Here, if you look into this, a complete zinc oxide nanorod. And if you look the structure, a very highly porous structure is being observed. If you look into this particular nanor, this is complete nanos. This is complete rod, zinc oxide nanorod over the surface. This is the BET analysis we have done. Zinc oxide shows 27 point average pore size 27.3 meter square per gram. Pan shows 16.46 meter square per gram. But when we decorate this zinc oxide over the pan, it goes to 98.05 meter square per gram. Thermal properties. As it is the inorganic material, it is highly thermally stable. But when we compare with the pan, the thermal stability of the pan nanofiber goes on increasing because of the decoration of the zinc oxide nanofiber. Then pan zinc oxide shows melting point 315 degrees centigrade, while pan shows 307 degrees centigrade. Means thermal stability because of the decoration of the zinc oxide over the surface goes on increasing. Now, mechanical properties. As material is highly stable, material is highly strengthful. This itself showing the tensile strength of that particular material. With increasing the amount of zinc oxide loading from 10% to 50 weight percent, thermal stability goes on increasing. Elongation is also goes on increasing. Young's modulus is also goes on increasing. Hardness is also goes on increasing. But hardness is somewhere seems to be deteriorated. This is because of the might be there is the agglomeration somewhere, or that may be the instrumental effect. That might be the instrumental effect. Now, application of this pan zinc oxide hybrid nanofibers into visible light photocatalyst. Photocatalyst, you know, is a substance uses the light energy. Light is being used to facilitate the chemical reaction. And when in presence of the light and water, what happens? Photocatalyst creates strong oxidizing. This is the complete. This is an example. Copper sulfate is being used as photocatalyst. There is a formation of holes and the electron. When visible light comes over the surface, this is one of the dye. This dye is getting degraded, and there is a combination between the valence band and the conduction band. Recombination is taking place. Holes, here the electrons, and when this is happening, reduction is taking place. This is the degraded product, and when in presence of the holes, the oxidation is taking place, and these are the degraded product is formed. This is how the change by minimizing or maximizing the band gap between the valence and the conduction band, we can easily use this material as a photocatalyst. So, application of the photocatalyst, these are acting as a sterilizing. If this can be sterilizing material, deodorizing effect. They use the effect of sterilizing, deodorizing, air purifying effect, anti-fogging and self-cleaning, water purification and dye degradation. Our aim is to use this material for the water purification and the dye degradation purpose. This is the example, base example, that is a chlorophyll, natural photocatalyst, which captures the sunlight to turn water, CO2 into oxygen and glucose. See, this is the solar rays come over the surface of the leaf, and this carbon dioxide plus water is converted into the glucose and oxygen. This is a complete photosynthesis process, effect of the photocatalyst. So this is the beautiful slide. Over 2 billion people belonging to 60 countries of the world are dying for water. By the year 2015, the figure may go up to 7 billion. Earlier, if we look into this crow, when he is in search of the water, he found this container. Into that container, the level of the water is very low. What he is doing is using and searching the stones and put the stone into that water. What happened? Because of the weight of the stone, water is get lifted and he easily take the water. But after that, what he is doing, he is not able to, he is not searching any stone. He is searching the straw. With the help of the straw, he is taking the water. With the help of this straw, he is taking the water. In the second case, what he is doing, sorry, net problem is there. Am I audible?
Yes, you are audible, but your screen is not visible.
Yes, just a minute. I will arrange.
Sure.
Hello?
Sure.
Yes, 1 minute.
Yes, now. No, it's still blank.
Just wait, sir. Just wait.
Sure.
मध्ये नेटचा प्रॉब्लेम होतो. माझे लावलेले आहे. एक मिनिट. बघते. Screen is visible, sir? Hello?
Yes, now it is visible.
Okay,
Oh.
sorry, because of the network connectivity, the slides are not visible clearly.
That's okay, no issue. We can understand that.
Okay. Now we are here. So in the third case, what the crew is doing is not thinking to sit over the edges of that particular container. Is directly sit near to the container and use the water to lift it, lift from that particular container. But if water will not be there, if no water in the container, in what way he will use to take the water? Means for the last 3 generations, our family was very scientific in managing the water problem. But what can I do when there is no water left? When there is no water left, what we will do? That is the big question. Okay. So these are the system. This is the industrial wastewater, which contain a very hazardous dyes in it. And if you think about this particular hazardous dye, they are very dangerous for our health. They are very dangerous for our health. So we have used different dyes for slides are moving, na? Slides are now?
Yes, sir, your slides are visible now.
Okay. So in the photocatalytic activity, we have used malachite green. If we look into this particular malachite green, we have used pan zinc oxide. If we look into only pan, there is a 24.8% degradation. If you look into zinc oxide, use 89% degradation. But when you use pan zinc oxide nanofiber, there is a degradation of this malachite green increases up to 96.3%. Same study we have performed with methyl orange. That is a pan gives 21%, zinc oxide gives 74%, while pan zinc oxide gives 90.3%. And when we compare both these dye, this pan zinc oxide nanofiber is very much selective for malachite green because its degradation rate is very high, that is 96.3% as compared to 90.3% in case of the methyl orange. Then we have done the photocatalytic activity without catalyst. If we look into this activity, 0 minute, 200 minute we have selected for methylene, malachite green and methyl orange. There is no degradation at all in absence of the catalyst. We have done the kinetic study also. And upon kinetic study, both these dyes shows pseudo-unimolecular first order reaction. They have followed the pseudo-unimolecular first order reaction. We have done the zeta potential. If we look into this, pan zinc oxide nanofiber is surrounded by the negative charges over the surface. Electrostatic stabilization is there. This is a cationic dye. Malachite green is a cationic dye. This is negative charges over the surface. And because of the negative and positive charges, malachite green shows the faster degradation as compared to methyl orange, as it has negative charges over the surface as well as negative charges over the surface of your pan zinc oxide nanofiber. So the slower degradation rate is there as compared to Mg to MO. Interaction between the dye molecule and the photocatalyst. Okay. When we check the zeta potential study, we found that it is more stable. Stability is more. The value comes nearby say in between 0 to 1.0 in negative form. Okay, so it is more stable even after the 3 to 4 cycle. This is the complete mechanism. We have used the different types of the we have used the quenchers. Without in absence of the quencher, it showed 97%. In presence of quencher isopropanol, it showed 46%. In presence of p-benzoquinone, it shows 52% mg. And in presence of EDTA, that is in presence of sodium complex of EDTA, it shows 65%. While about MO, that is methyl orange, it shows 90% without quencher, and shows 44%, 48%, 63% in case of the another quenchers types of whatever the quenchers we have used. So this is the reduction which is been happened formation of the holes to the electron. There is the increase in the band gap. Shows the high degradation in case of the malachite green. This is the reusability study we have done. We have used this nanofiber, washed up in the first cycle. After first cycle, we have washed the nanofiber. Second cycle, we have washed it. In third cycle, we have washed it clearly. And after repeated washing, we are using this nanofiber continuously up to fifth cycle. And when we compare from first, second, third, fourth, and fifth cycle, Mg shows marginal decrease in the rate of degradation, while in case of methyl orange there is a marginal decrease but maximum decrease at the fifth cycle. Means Mg malachite green is very responsive and very selective in case of the pan zinc oxide nanofiber for the degradation purpose. Degradation efficiency of Mg and MO dye after each consecutive cycle we have studied, and it shows a very good response. After reusability, we have done this morphology study. If we look into the morphology, it does not lose its structure. Nanofiber seems to be very clear. If we try to go after fifth cycle also, there will be the degradation, but the rate of degradation will be nearby. So we have stopped to fifth cycle only. FTIR after degradation shows same presence of the same functional group, or that is degraded methyl orange and degraded malachite green. These are the degradation of this particular group, shows the separation of that functional group is been observed. Comparative study we have done. People have used pan zinc oxide nanofiber. They have studied with methyl orange. 10 hours they have required. Somewhere 240 minutes, but we have used pan zinc oxide nanofibers for malachite green and methyl orange. Shows 200 minutes and 280 minutes only. This is the present work as compared to the others. Then we have done the characterization of this is the comparative study for the present work. Am I audible, sir?
Yes, you are audible.
Yes, okay. Now, characterization of pan AGG hybrid nanofibers. So this is the XRD we are done, XRD and FTIR. If we look into this XRD and FTIR, silver graphited nanoparticle shows these are the crystal planes. Pan shows 2 crystal planes, and upon decoration of silver graphited over the pan nanofiber, there is the combination of both the crystal planes. It suggests that formation of pan AG silver graphited nanofiber. While if we look into this particular FTIR, the presence and combination of the functional group showing that formation of pan AGG nanofibers. In XPS and FACM study, XPS is also in a line with the study and the experimental data. experimental, whatever the experiment we have performed. That is a deconvoluted spectra is being shown into the inside of the second figure, and the same images showing the silver graphite plates. Over that graphite plates, silver is getting decorated uniformly. PAN nanofibers seems to be very uniform with uniform thickness and uniform size. And upon decoration of that particular PAN AGG nanofiber, you find the increase in the porosity of that material. This is the TAME image. That TAME images is showing a very highly porous structure of the material. And EDAX is showing the presence of PAN group and your zinc oxide. That is AGG nano particles over the surface. Thermal stability, PAN AGG shows seems to be highly thermal stable as compared to your PAN and silver graphitic nanoparticle. This is the mechanical property. As like mechanical property of PAN zinc oxide nanofiber, because of the decoration of silver graphite nanoparticles over the surface of the PAN, the thermal properties like tensile strength, elongation at break, Young's modulus, hardness goes on increasing. Now, next, PAN AG graphene nanofiber as a photocatalyst under solar irradiation. This is the application we are studying. We have used here methylene blue. Methylene blue we have used here. And in the methylene blue, if you look into this PAN to silver graphite nanoparticle, it shows the degradation 25% to 79%, but upon decoration of silver graphite nanoparticle over the surface of the PAN, it shows 88.1% degradation. While in case of methyl orange, 24% for PAN and 74% for AG silver graphite nanoparticle, but it shows 82% for PAN AG nanofibers. And when we compare with both methylene blue to methyl orange, the rate of degradation is more in case of the methylene blue, that is 88.1%. That is the effect of the electrostatic charges over the surface of from methylene blue to the surface of the PAN AGG nanofiber. This is the photocatalytic study without catalyst. If we look into this, there is no degradation at all. This is again showing the pseudo-unimolecular first order reaction. We have done the kinetic study also, pseudo-unimolecular first order reaction. This is the degradation mechanism. And this is the reusability and type of the quencher use along with the TOC remol we have done. Then if you look into this reusability study, we have used again this catalyst up to 5th cycle. And even at the 5th cycle, degradation of methylene blue is more, up to 91% as compared to methyl orange. And in case of upon using the quencher, it shows 88% without quencher, 88% degradation in case of the methylene blue and 82% in case of the methyl orange. After reusability, we have done the XRD and FACM. If we look into XRD, FACM and FPR study, there is no change in the structure of the material. It doesn't lose its structurability. It seems to be stable as like in the first cycle. Porosity is remain as such, but some porous structures, some pores are get blocked because of the number of washing with the help of some acid or like this. But if we look into other surface, this other surface is very clear. Means we can go ahead for the 7 cycle also. This is the comparative study. PAN AGG nanofibers and PAN AGG nanofiber for NB and MO shows the degradation at 75 minutes and 90 minutes under solar irradiation. Then PAN AGG C3N4 hybrid nanofibers. This is the XRD and FTIR. XRD FTR suggesting the formation of pan AGG C3N4 nanofiber. This morphology is showing the formation of AG. The first image is showing AGG C3N4 nanoparticles. Second one is for the pan nanofiber. And if we look into this, another two peaks, that is formation of pan AGG C3N4 nanofibers. This is the same EDS mapping of pan AGG C3N4 nanoparticle. Very uniform and very fine decoration of the material is being observed from the same EDS mapping. XPS is also showing the formation of that particular nanofiber. This is the TAME image. The TAME image is clearly showing the decoration of silver graphite carbon nitrate nanoparticles on the surface of the pad. This index is showing the presence of that elements, that is nitrogen, oxygen, and silver, carbon from the C3N4, silver, and pad. Now we have used this material for the visible light driven for the selective oxidation of styrene, CH2 bonded molecule, and benzene. First, we go with the styrene oxidation. As a catalyst, we are using this material. If we look into this, this is the styrene under the normal light and H2O2 as a H2O2. There is a formation of styrene oxide, benzaldehyde, then phenylacetaldehyde, and benzoic acid. There are the 4 products, and these 2 products are a major one, and these 2 are the minor one. If we look into this pan AGG C3N4 in presence of CH3CN as a solvent, time required is 16 hours only, and total conversion of all these products is 98%. But if we look into styrene oxide, it gives 60%, benzaldehyde gives 32%, while phenyl acetaldehyde shows 7%, and benzoic acid is only 1%. Means this catalyst is very much selective for styrene oxide. It gives 60%. Catalyst screening and reaction optimization we have done. We have changed the alkyl group here. R group we are changing. Phenyl, methyl, bromine, chlorine, and NO2 we have changed. When we look into the conversion, it goes 98% in previous 2 cases. In another case, in presence of bromine, it shows 97%. In case of chlorine, it shows 81%. In case of NO2, it shows 72%. But if you go with the selectivity study for the change in the group, R group, alkyl group, CH3, it shows selective towards the styrene oxide of 65%. It gives 65% as compared to the other 3 to 4 cases. Then we move to the next, that is a CH oxidation of ethyl benzene. In CH oxidation of ethyl benzene, this is the ethyl benzene. Catalyst is being added. Normal light is being used. H2O2 as the oxidizing agent. There is a formation of that ethyl benzene. We have taken 1 mole, and there is a conversion of ethyl benzene to acetophenone. Conversion of ethyl benzene to acetophenone. If we look into our case, pan AGG C3N4 nanofiber in presence of cyanide CH3CN, 12 hours is required, shows 98% conversion, complete 98%. Only single product formation is there, no byproduct is there. These are the different derivatives we have done their conversion, ethyl benzene to acetophenone. Selectivity 99%. In maximum cases, the selectivity is 99%. If you look into this product, 99% to 98% selectivity is there. Conversion is from 94 to 99%. Then CH oxidation of benzene. In CH oxidation of benzene to phenol. Benzene to phenol. Here 30 minutes is required, conversion is 99%. And this is the scalability study. 3 millimole of benzene in presence of the catalyst, in presence of the solvent, in presence of the oxidizing agent, it gives 86% conversion. 86% conversion means gram scale reaction was conducted using 0.228 gram of benzene. The scale up reaction afforded the phenol with 86% in after 30 minutes. Only 30 minutes is required for the conversion. This is the reusability study we have done. In reusability study, we have used this catalyst up to 8 cycles. Even up to 8 cycles, there is a marginal decrease in the conversion of that particular product. Okay. Silver concentration before reaction is 4.56%. See, whatever the TM images is being shown to the last E and F images, the silver concentration before reaction was 4.56%, but after reaction, after reusability, silver concentration of the concentration over the surface is 4.55%. Means 0.01% was removed from that. Only 0.01% of the silver is being removed from that particular surface. Now, next is the copper nickel carbon nanofiber. As I mentioned, we have used the concentration 2:1, 1:2, 1:1. We have done the synthesized copper oxide carbon nanofiber, nickel oxide carbon nanofiber, only the carbon nanofiber we have done. And then we have used the conversion with this particular this ratio. And if you look into this, the combination comes, the formation shows itself the copper nickel carbon nanofiber. Okay. This is the XPS study. That is for carbon nanofiber, nickel carbon nanofiber. This XPS study, presence of deconvoluted spectra showing the formation of that respective ratios of copper nickel carbon nanofiber from 1:2, 2:1, 1:2. These are the deconvoluted spectra. We have separated it out from the convoluted spectra to deconvoluted spectra. This is the TGA study. If we look into the TGA study, this ratio is showing maximum thermal stability as compared to the pure nickel oxide carbon nanofiber, copper oxide carbon nanofiber, and carbon nanofiber. And mostly 1.1 and 1.2 shows the maximum thermal stability. This is the Fescm study. These are the carbon nanofibers. First is the carbon nanofiber. Second one is the copper oxide carbon nanofiber, nickel oxide carbon nanofiber, and copper nickel carbon nanofiber. Complete plates are there. Very thin rods are there. Patches are there over the surface. This is it's a high resolution transmission electron microscopy we have done. And if you look into this, the dark patch is of copper, light patch is of nickel. The combination is uniform throughout the fiber structure. And we have done the cyclic voltammetry study for this. If you look into the cyclic voltammetry at scan rate of 5 millivolt second inverse, this copper nickel of 1% shows maximum current flow, shows maximum. If we look into this loop, here again 20 millivolt per second of copper nickel carbon nanofiber at 1:1, showing the varying scan rate from 5 to 200 millivolt per second. We have done the galvanic charge discharge curve, study the same. If we look into this, 1:1 is showing maximum charging and discharging up very later. But other two cases, charge very fast, but discharge very fast again. Discharging is very fast. But here charging is fast, but discharging is very late. This is the GCD curve of copper nickel carbon nanofiber with varying current density range from 1 to 50 ampere per gram. We have done the cyclic stability, and cyclic stability is more in case of 1:1 as compared to the nickel copper nanofiber and copper nickel nanofiber. We have done the Nyquist loss also. In Nyquist loss, again 1:1 is showing a very good range of stability towards the galvanic charge discharge case. So conclusion, electrospinning technique was used to fabricate pan-based nanofiber. The electrospinning parameters which are optimized, we have optimized the different parameters like electrical field, distance between the needle and the collector plate, and polymer concentration of the polymer. Due to decoration over the surface of the nanofiber and high specific surface area, these pan zinc oxide nanofiber shows good response toward the degradation of malachite green and methyl orange dye. But malachite green shows maximum degradation as compared to methyl orange. The same case is observed in case of pan zinc oxide nanofiber or even up to the 5th cycle. We are very fortunate to have these results are very impressive when we are using the bare to the decorated material. Which shows a very good responsive degradation in case of methyl orange, malachite green, methylene blue dyes as compared to the other methyl orange, as well as when we use the advanced material for the purpose of the oxidation of some organic materials, they are seems to be very effective and very selective for that particularly for styrene oxide, and mostly in case of the benzene it gives the phenol to 86% even up to the 8th cycle. Copper nickel carbon nanofiber at different ratios shows uniform size range with effective size range is 1:1, which shows the impressive electrochemical behavior was observed at current density of 1 ampere per gram compared to carbon nanofiber. These are the future scopes for the particular study. Thank you very much. So this is the galvanic charge discharge curve for the material. If you look into this charge discharge, 1:1 is showing the maximum charging capacity with very late discharging capacity as compared to 1:2 and 2:1 ratio. This is the cyclic stability of the. Already I have discussed this conclusion. These are the future scope for material. Thank you very much.
Thank you so much, sir. Thank you so much, sir. It was a really very well explained and informative session. And it was really interesting how you explained the technique of electrospinning and then optimization of the different parameters and different methods for the fabrication of nanofibers and afterwards their applications. The most remarkable thing about your session, which I guess all the participants will also agree with me, it was you also explained how we can infer the different type of data that we are obtaining from the characterization technique, material characterization technique, like the graphs, how do we infer results from them, how do we analyze the images. So thank you so much, sir. It was really informative session. And last but not the least, we all enjoyed the Thirsty Crow story that you restated in the modern context. So thank you so much. Now let us take a question from the chat box. So here I have a question from Remya R. Nair, and she's asking, sir, can you please explain the techniques used for the measurement of hardness, tensile strength, and Young's modulus of nanofibers? Very delicate nanofibers are getting from electrospinning technique. So how can we increase the mechanical strength of these nanofibers? I guess she has posted so many questions. Then the third question is characterization of electrospin PVDF nanofiber, usually piezoelectric measurements of PVDF polymer fiber with some additives like TPU, CNT, graphene, etc. for energy harvesting. They are the main area of their research. So these are the questions from her side.
Okay, I just explain one by one. First question is that measurement of hardness, tensile strength, and ink modulus of nanofiber. Hardness can be measured with the help of the hardness tester Shore D and Shore A. Okay, and tensile strength and ink modulus can be measured with the help of the universal testing machine. Only the load cell will be different for the nanofibers. Okay, load cell is of 50 kilo to 100 kilo. You can change accordingly as per the ASTM standard. Then for electrospinning technique, how can we increase the mechanical strength of this nanofiber? See, this is depending upon the way, in what way you are drawing the fiber from the electrospinning technique. You have to maintain the viscosity. You have to maintain the distance between the collector plate and the tip from where the solution comes. And second major thing is that the flow of the solution from the needle. If we maintain all these three, all parameters, there will be no any node formation or gel formation. If no node or gel formation will be there, your fibers of a very high strength material. Okay. For characterization of electrospin PVDF nanofiber, usually piezoelectric measurement of PVDF polymer nanofiber with some additives like TPU, graphene, etc. for energy harvesting are our main area. Okay, that is your area. That is not the question, I think so.
Yes, sir.
Okay.
So thank you so much, sir, for sparing your valuable time for us. It was really a pleasure to listen to you throughout the 2 sessions of this day. Now I declare the end of this session here. One participant is asking for your email contact, sir, like for further queries.
Yes, I have given my slide on my slide. Okay.
So actually through this training program, we are targeting the MSc students and PhD scholars basically. So, sir, your voice is not coming.
Am I audible, ma'am?
Yes, sir. Now you're audible, sir. Yes, sir.
Okay.
Sir, we received your email ID in the chat box. So once again, thank you so much, sir. I thank all the participants here. Soon you will be sent the email IDs, the joining links for tomorrow's session. So I declare the end of the session here.